Hi, welcome AP students to your enthalpy calculation AP problem walkthrough. We're going to do one conceptual. I kind of introduced already heat of formation overall equation, method one for calculating the enthalpy of a reaction. I have introduced Hess's law at the end of the lecture yesterday and walked through a conceptual problem yesterday and the AP problem. And today I'm just going to address conceptually the final way that we could calculate the enthalpy of a system via approximation through structural formula or bond breaking versus bond forming calculations. And then we're going to hop into two FRQs. So for the bonds breaking and bonds forming estimation, please keep in mind that it really is an estimation. Like this is the least accurate out of all three of the methods to calculate the enthalpy change of a system. So when you're doing this, what you want to identify is the number, the amount, and types of bonds being broken. So for this problem, we see that we have the following bond be broken, and that is your C3CH bonds are being broken, okay, from reactant to product, and it's 2 moles of 3CH. So, so you have also, by the way, this coefficient of 2 in front means that you're going to have 3CH bonds, 2 moles of 3CH bonds that you're going to break. Okay. So how would you write that? For acknowledging the bonds broken, you would write 2 times 3CH bonds broken, whatever that value is. Okay. And then we're going to also identify the bonds broken in the other molecule, which is going to be, we're going to break 3 NH bonds. Okay. And notice this also has a 2 in front. So we're going to write 3 NH bonds are broken in our reactants. And then when we look at the product, we notice that we are also breaking the double bonded O. And there are 3 moles of that. So we would write that we have 3 moles of double bonded O that we're breaking. Okay. Now let's then identify the bonds formed. And then we'll put this into our overall equation. So bonds formed. Okay. We are going to see that we have a CN bond form. So, and we get 2 moles of that CN bond form based off the stoichiometric ratio. So 2C triple bonded N, okay, is formed. And then we also see that 2 OH bonds are formed at a 6 molar ratio. So we'd say 6 moles of 2O single bonded H, okay, bonds are formed. And so then what we would do is after identifying the bonds formed and bonds broken through this estimation process and using the structural formula, i.e. the Lewis structure diagrams, what we would do is we would put it into our equation that for estimating via bond energy, we put that the enthalpy of the system is equal to the sum, the sum of bonds broken minus the sum of bonds formed, which makes sense because we always input energy to break bonds and we always release energy to form bonds. So that's why we are subtracting the forming of the bonds, the releasing of energy from the breaking. Okay. And what we would get then is we would simplify our work done up here and translate it to the formula. So we would say that it's going to be bonds broken sum is going to be 6 times CH bond value breaking bond energy value, okay, plus 6 times the NH single bond energy value, plus 3 times the double bond oxygen breaking value. And don't forget bond energy, by the way, just a reminder that bond energy is the energy it takes to break a bond, which is indicative of the amount of potential energy stored in the bond. All right. So the stronger the bond energy, the more stabilizing the bond, right? Or the higher the bond energy, the more stabilizing the bond. So don't forget that when we look at these values, these numbers also represent concepts that you should be familiar with and understand. So that is the sum of our bond breaking that we've identified multiplied by the respective stoichiometric coefficients. And we're going to subtract bonds formed. So we've identified that 2 C triple N bonds are going to form, and 6 times 2, 12 single OH bonds are going to form. And so what we get, and that's going to equal the enthalpy of our system. And what this adds up to then is 6 times 413 if you use the table next to me on the right side. 6 times 413, right? Which we would find is the CH plus 6 times, where's the NH bond? 391 plus 3 times, where's the double O, double O? 3 times O2, 498. Okay. All that sum together minus 2 times C triple N. 6. Oops, I don't think that's triple N. Triple N is actually 891. It is over here. Plus 12 times O single H. 467. Okay. And what we would do then is we would add all this together, subtract the respective sum of the bonds formed value, and we would get a value for the system, an estimated value for the enthalpy of the system, for which is this particular reaction with this particular combination of bonds breaking and bonds forming, or the bond rearrangements, is exothermic with a negative 1.068 kilojoules per mole. And that would be how we solve this. So let's now head to our AP problems. Sorry, guys, I'm competing with a leaf blower. Okay, so we go to AP question 3, and it's a short FRQ, which means it's take about 9 minutes, and it's worth 4 points. So we have the equation given below, and it's the combustion of ethane. Oh, actually, ethene. Ethene is a technical term for this, so it would look like this compound. It's an organic chemistry molecule, and it's represented by the equation below. Use the enthalpies of formation in the table to the right to calculate the overall enthalpy for this reaction under standard state condition tabular data. So what we would see is that for determining the enthalpy of our reaction via standard state tabularized individual heat of formations, we say that it is the sum of the enthalpy of formation of the products multiplied by their respective coefficients minus the sum of the enthalpy of formation of the reactants multiplied by their respective coefficients. Okay. And so what we would get is that the enthalpy for this reaction, given the data, is our products are going to be 2 CO2s, and CO2 requires an energy of negative 394 to form. kilojoules per mole plus 2 H2Os, which is negative 286 kilojoules per mole. Okay. All of that added together, minus, and I realize I did not leave myself enough space, minus 1 C2H4 reactant. So that's 52 kilojoules. Added that to 3 oxygens. Now, oxygen is a diatomic. It's in its pure elemental state. So we would actually say 3 times 0. And you didn't even need the table to give that to you. You should have known that. Okay. And so what you do is you would add this up together, and you should get a value that the heat of the reaction is equal to negative 1412 kilojoules per mole of reaction, representing an exothermic reaction in a molar value. So we would call this a molar enthalpy, right? Because it's written per mole. Almost every single enthalpy that you'll ever be provided in the AP is a molar enthalpy. Okay, moving on to the next problem. Here we have the energy of the reactants is shown on the energy diagram above. On the right side of the energy diagram, draw a horizontal line segment to indicate the energy of the products. Draw a vertical line segment to indicate the enthalpy of the reaction and label it with the correct value. So obviously there's going to be some activation energy going on here. You don't know what it is, but you do know that wherever the activation energy takes you, the final products should be lower in potential energy than the reactants. Okay, so that means that the potential energy of your products, if it's exothermic, is less than the potential energy of your reactants, reflecting a net overall loss of energy. So you should draw a line lower, okay, for your products. And maybe you can even label it products. You could even put the products, if you wanted to, you could label it as CO2, H2O, right? I don't know why I had to look that up, because combustion always makes CO2, H2O. And then what you would do is you would say that the distance between your reactant potential energy and your product energy is your enthalpy that you determined, which is negative 1412 kilojoules per mole. Okay. And I'll move this down here just to kind of reflect. That's how we did our thinking. Okay. Please note that you definitely have no info on activation energy. So I just drew it into so you can see that this is a potential energy diagram, but you would not be able to accurately represent this fully because you don't know anything about the activation energy. Okay. And all it was really asking you was for this, right? This is what it was asking you for here and here. Okay. So moving on, based on the information above, so this provided here, identify the enthalpy values that should be added together to determine the values of enthalpy for the entire reaction for the following reaction. So what it's asking you to do here is that you need to create this is your net reaction that you need, okay, to create a kind of like algebraic sum, enthalpy of formation summation, Hess's law. This is a Hess's law problem. Okay, so what it's asking you is, okay, given the previous information throughout the entire prompt and this newer information, what should occur, what value should be added, and how should they be added together to get this final net equation? So if our goal is to get this equation, first of all, we have to look at the equations that we've been provided. We've been provided the equation above, okay, C2H4 plus O2 goes to 2CO2 plus, okay, plus H2O plus 2H2O liquid, and I am going to specify the state of matter for water because water is such a common compound to be in various states. And then I was able to determine from part A the enthalpy of this reaction, which is negative 1412. And remember, if you got part A wrong, but you do part C that I'm walking through right now correctly, you will only be deducted a point from part A. So keep that in mind, guys, because a lot of these future portions of FRQ hinge on your prior work, right? So that AP doesn't punish you for future work as long as you do the correct logic. It only punishes you for the original mistake. Okay, so that was from part A. Now we're given in this new prompt, we're given, okay, part C, we're given this new equation, C2H5OH, okay, plus 3O2 goes to 2CO2 plus 3H2O liquid, right? Now, if we look at this equation, these two equations, and we compare what we want, okay, what we should notice is the elements that we want are all present between these two reactions, okay? H2O, okay, H2O, and C2H5OH and C2H4. But the problem is, what we immediately also notice is that it's in the wrong ratios. If we were to sum up these currently as written, I would have 5 H2O on my product side, and I'd have my desired product C2H5OH on my reactant side, which doesn't make any sense. I'd also have O2 still present. So what we're going to do is do some algebraic manipulation of the chemical reaction. So what I'm going to do is I'm actually going to flip, okay? I'm going to flip this part C equation, and now I'm going to write it as, okay? So I'm going to flip this. I flip, which means I'm going to flip the sign for my value. Okay, so what I get then is 2CO2 plus 3H2O liquid goes to the reverse reaction, C2H5OH ethanol and 3O2. And that means that my enthalpy value is now going to be positive 1370. And when I flip it like this, I notice that my, okay, desired product, C2H5, is now on the correct side. I also noticed that when I add up the sum of this, my O2s, okay, don't quite cancel out. I have 3O2, okay, on bottom, but I don't want any O2. Now, did I miswrite any of this? Oh, I totally miswrote that I actually have 3O2 as well. Okay, perfect. So I totally mistranscribed the first equation from part A. So now what we see is perfect. This is working out. My 3O2s cancel because they're found both on the reactant and product side when I sum these two reactions from part A and this part C. My 2CO2s also cancel, which is what I want because I don't want it in my overall net equation. And two of my H2Os cancel, leaving me with one H2O. And then what I get for the sum reaction is C2H4 plus one H2O liquid on the reactant side produces 1 molar of C2H5OH. And I did indeed produce my desired, okay, net equation. So now what I do is I sum up the enthalpies, having made sure I reflected any change or multiplication that I did to any reaction. So for part C, since I flipped it, I flipped the sign, and I get that my value, okay, to be added together is 1412 and negative 1412 and positive 1370. All right, giving me a value of oh no, negative 42 kilojoules per mole. Okay, so you could have answered this verbally by saying that describing the enthalpy of negative 1412 kilojoules per mole from part A should be added to the flipped enthalpy of, I'll write the value, flipped enthalpy positive 1370 kilojoules per mole from part C. You could have also done it verbally. I don't know how well you would have been able to identify just looking at it without kind of doing some of the math anyway, but that's also a possibility. The AP would consider your work above as a justification in answer to the question. Okay, so that's short FRQ 1. Let's go to, or question number 3. Let's go to long FRQ number 4. So what we have here is we have hydrogen peroxide decomposition, and we're asked, okay, a particulate representation of the reaction is shown below. In the box below on the right, draw the particulate representation of all the molecules that would be produced from these 4 reactant molecules. So what we have here is we have 1, 2, 3, 4 H2O2, which means it would be like, to keep the same ratio, represented in the balanced chemical equation. If I have 4 H2O2, that means I'm going to get 4 H2O and 2 O2 based off of my starting material. So I should draw H2O, okay? And they kind of give you a key of how they want you to draw scale-wise and shading. So I should get, copy 4 waters around, and I should also get 2 oxygens, diatomic oxygens, okay? And I didn't do that quite to scale, but there we go. And that would be question number part 1. And then what I have here is shown below is a potential energy diagram for an uncatalyzed decomposition of H2O2. According to the diagram, is a decomposition reaction exothermic or endothermic? Justify your answer. This is like a dream long FRQ, guys. This is like family favorite right here, family friendly, okay? So what we have here is this reaction is exothermic, okay, as evidenced by the products demonstrating a lower potential energy arrangement than the reactants. Thus, the system experiences a net release of energy. Okay. Manganese dioxide, MnO2, is an insoluble substance that acts as a catalyst for the decomposition reaction. So remember, catalysts, right, are consumed and then regenerated or produced. Just a quick reminder, are regenerated, then produced. On the diagram above, draw a curve to represent the reaction as it occurs in the presence of MnO2. Remember, catalysts always lower the activation energy by offering, I don't know how to spell offering, but that is totally okay. Offering an alternate route, okay, an alternate mechanism. So what you might do is you might, while the reactants stay the same, your overall activation energy would be lower, okay, but it would still lead to the same product arrangement. So that's the same product potential energy, okay? All right, moving on. A student investigates the decomposition reaction in the laboratory. The student prepares 2 small beakers, adding 20 milliliters of 9.77 MHO2 to each one. So each beaker, sorry guys, my timer went off. Each beaker is placed on an electric balance. The students add 0.10 grams of MnO2, our catalyst, to the second beaker and records the mass of each beaker and its content at 10-second intervals for 1 minute. If you are catching on, this is totally a rate law based question based on actual data, right? The beakers in the data are shown below. So quick reminder, don't forget that rate law can only be determined experimentally, right? We have a ton of approximation methods where I taught you kind of fancy math, art, yes, but in the end, to get the accurate rate law for a reaction, you do have to just test it out in lab. So what we're seeing here is a rate law question for beaker 2 during the 60 seconds. And remember, beaker 2 is the one with the catalyst. So theoretically, you should be seeing more product form. All right. And if we see here, then for beaker 2 during 60-second period, calculate the following. Okay. So the number of moles of O2 that was produced. All right. So what we see here is that in the 60 seconds, we see that when you look here, mass 2 versus H2O2, aqueous. Okay, so H2O2. So when we look at this original reaction, the unique thing that we're measuring is kind of hard to measure necessarily the water amount, right? So what we're really measuring is the O2, right? So that's kind of like the unspoken here product that we're actually measuring, okay? And when we're putting our focus on, because it's kind of hard to measure the production of water in an aqueous solution, all right? Even though that is technically one of the products of the decomposition, okay? And so what we're going to do is we're going to say that we're going to look at the comparison of the mass, okay? And we know that we can't really measure gaseous oxygen. So what we're really going to look at is how much mass was lost in the 60-second interval. That's going to be indicate the amount of O2 produced because we're in an open system. Notice there's no lid here. And because we're in an open system with no lid where gas will escape. And that gas escaping is representative of mass escaping, okay? And therefore O2 escaping, and therefore amount of product being produced. So we would say, let me make this a little smaller. Okay, so when we do this math now, we would say, well, in beaker 2, in the 60-second interval, I have a mass of 43.19 at the beginning, but at the end, I have a mass of 42.58, giving me, okay, a mass of O2 equal to, let me make this a little bit better. Oops. Spread it out a little bit. A mass of O2 of 0.61 grams. And then I'm asked for this value in moles. So I do 0.61 grams of O2 times for every mole of O2, molar mass, I have 32 grams, giving me a mole value of 0.019 mole of O2 is produced based off of the loss of mass, right? O2 gas. Okay. So then what is the mass of H2O2 that decomposed? Well, I know that if I produce 0.019 moles of O2, and for every 1 mole of O2 produced, I decompose 2 moles of H2O2 based off of my balanced chemical reaction shown above. right? O2, 2H2O2. That I would get the mole amount, that particular mole amount of H2O2, right? But I'm not asked for it, the H2O2 value in moles, I'm asked for it in grams. So I'm going to use the molar mass of H2O2, which is 34.02 grams of H2O2 for every 1 mole of H2O2, okay? Which would give me a value of 1.3 grams of H2O2 decomposed. Okay. And so that is how we would solve that problem. D, the student continues the experiment for an additional minute. For beaker 2, with the mass, will the mass of H2O2 consumed during the second minute be greater than, less than, or equal to the mass of H2O2 consumed during the first minute? So essentially the idea is, what we're being asked here is that, are we going to have essentially a constant rate of consumption or decomposition of H2O2, right? Is the amount that I consume going to be equivalent in minute 1 as to minute 2? And we know from our discussion, our beginning discussions on kinetics, that there's a reason when we do experimental data that we always take initial rate, right? Don't forget, with experimental data collection for rate, we always take the initial concentrations and rates, because we know as time goes on, you simply run out of product, which naturally statistically lowers the collision frequency and therefore lowers the rate. Not because anything inherent in the reaction, just simply because you're running out of particles to react. So we would say that the mass of H2O2 in minute 2 consumed would be less than the mass of H2O2 consumed in minute 1, because, okay, over time, there is less reactant present in the system. Therefore, slowing, okay, the rate of reaction as evidenced in the mass, right? As evidence in the, when we look at the reaction here, as evidence in the mass change getting smaller and smaller each 10-second interval. Evidence in the change in mass decreasing over the sequential 10-second intervals. Notice here, they do want you to use the data to back up your concept, okay? So based on the data, in the student claims that the catalyzed reaction has 0 order kinetics. Do you agree? So remember, for 0 order kinetics, that would mean that the concentration of your reactant has no impact on rate. And for us, how are we finding the rate? Our rate is indicated through mass change in this problem. Like, we are examining the rate by tracking the change in mass of our beaker, okay? For a 0 order, this would have to be true. But we notice that the rate is changing, or the mass change is changing, we're getting smaller and smaller increments of mass change as the concentration of H2O2 is decreasing. So we would say disagree because our reaction shows a decrease in mass change, okay, over time, which decrease in mass change over time, which reflects rate of reaction, okay, right, which reflects rate of reaction with decreasing H2O2 concentration, okay, with decreasing H2O2 concentration. For a zero order reaction, the rate of change or the rate of mass loss for a zero reaction, the rate of mass loss would have stayed constant. Okay, excellent. So F, we're almost done. We just have F and G. A second student did the experiment using larger volumes of, so just more, of 9.77 molar H2O2. The student noticed that the reaction in beaker 2 proceeded extremely rapidly, causing some of the liquids to splash out of the beaker onto the lab table. Okay, some of the liquid is splashed out onto the lab table. So that right there is mass loss. Okay. The student claims that as a result of the loss of the liquid from the beaker, the calculated number of moles produced is greater than the actual number of moles actually produced in the first 60 seconds. Do you agree? Yes, we definitely agree. So we agree because the mass loss is being used as an indicator of O2 production. Okay. Thus, with the additional loss of liquid, that's what the additional, the student, I guess you could say the student would be subject to overestimation of O2 produced. All right. Finally, G, the hydrogen peroxide used in this experiment can be prepared by the reaction of solid ammonium peroxydisulfate with water. Okay. The products are hydrogen peroxide and ammonium bisulfate, right? The balanced chemical equation for this reaction. So what we see here is that you would be given the reactants NH4 2S2O8 reacts, okay, with, and let's see, the reaction of solid, so it'd be solid with water, liquid. Remember, there's no such thing as aqueous water. That's kind of weird. Just write liquid water, okay? Oof. To produce H2O2, aqueous, and ammonium bisulfate, which I'm going to also assume is aqueous because you're in water. Okay, and then you'd have to balance it. So when you balance this reaction, what you would get. Okay, so that would give you I don't really feel like walking you through how to balance. This is totally like within your capabilities. So it would give you a coefficient of 2 in front of the water and a coefficient of 2 in front of the ammonium bisulfate. You could have written out this overall equation. You could also technically write out the net equation as long as it's balanced. It asking you for the balanced chemical equation and it's not asking you specifically for net. So I would just stick with the overall. And that's the end of this walkthrough. So really good job, you guys. And best of luck.